So I'm told that today is lecture 5 of battery fundamentals. So we've been meandering all over the place, and today we'll do some more meandering. The next time will become more formal. So I'm just laying the background. So today I want to talk a little bit more about chemical reactions and electrochemical reactions and some thermodynamics. So that's what we'll do today. So a simple chemical reaction. So let's discuss that first. Simple chemical reaction. So suppose you have metal A and metal B. So A is a metal plus B metal gives you AB alloy. So this reaction has what's called a driving force. So we have a little noise over here. So okay, so that's fine. Okay, so we mean room temperature, which is 298 Kelvin and 1 atmosphere pressure. And these compositions are some sort of, okay, composition doesn't matter because these are just metals and alloys. So for this, driving force will be the delta G naught of formation of AB minus delta G naught formation of A minus delta G naught formation of B. So what I'm doing is I'm basically writing over here. If I put this in more generalized form, I'm saying sum of the delta G formation of products minus the sum of delta G formation of reactants. So what we do is we take the products and we say how much Gibbs free energy does it take to form this product, and then so that's the sum of, in this case we only have one product, it could be more, so we sum all the products, the Gibbs free energy of formation. Then we subtract the Gibbs free energy of formation of metal A and metal B, and we can say that this metal A Gibbs free energy is 0 and metal B is 0, because those are metals you have with you. So one can say, to simplify this, that Gibbs free energy of formation of AB, that'll be the driving force for this reaction. And as I said, right now we haven't studied Gibbs free energy. Hopefully we'll do that today. So this is just a chemical reaction. And to put it in a different form, we can also say, so we have metal A and we have metal B. Let's put them in contact. So there's physical contact between them. So as a result of that, they'll be alloying. So with time, we will have an alloy forming AB between them, and then this boundary will move, and ultimately the whole thing will be AB. So this is just a chemical reaction. So now, but we are discussing electrochemical reactions. So let's discuss electrochemical reaction of A and B. So now we change it because we have electrochemical cell now. So we have metal A and we have metal B, and in between we have an electrolyte. And let's connect an electrical wire to connect between A and B. So now let's suppose that A plus ion is dominant. We'll also have the B plus ion, so let's ignore that. We don't have to, but it's easier, just say A plus is dominant. So A plus will enter the solution, and when we lose one A plus, we lost one electron, so that electron has to go that way, and then when this A plus comes over here, it meets up with that electron. So it's interesting that this ion oxidation gives you an electron, and then the A plus reduction, the electron combines with the ion to give you atom A. So as a result, what will happen is that this B will reduce and AB will form over here, and this A will also become skinnier, so more and more A will go in that direction, so that ultimately we will have all AB over here and just electrolyte over here. So this is just a thought experiment, right? So notice that by this chemical reaction, we combine A and B to give us AB. By electrochemical reaction also we got AB. And the driving force is still the same. So whether we did a chemical reaction or electrochemical reaction, we got the same driving force. So just to recap, the electrolyte is an electronic insulator. So I'm just recapping. So the electrolyte is an electronic insulator. So it acts as a filter. It only lets ions move through it, no electrons. And of course, the electrodes are electronic conductors, and the electrolyte is an ionic conductor. So with that, what I want to do is that now I say, oh, what about potential? So far we only discussed the chemical driving force. So this is our chemical driving force. So this, you can actually look up chemistry handbooks and find out what is the Gibbs free energy of the product, what's the Gibbs free energy of the reactants, and you can get this value just by looking at chemical handbook. But where does potential come in over here? So to emphasize, whether I'm doing a simple chemical reaction, and from that simple chemical reaction, I can look up the tables and get the Gibbs free energy, or I'm doing electrochemical reaction and forming the same product AB, it's the same Gibbs free energy. So this would be in, what would the units be? Units would be, let's say, joules per mole of the material. So mole is a quantity, J is the energy. So that's the Gibbs free energy. So how do we go from Gibbs free energy to knowing what is the open circuit potential of a cell? So this is stuff that's not covered in books. So what I'm trying to prove is this equation. Delta G of reaction under standard conditions is NFE. So this is what I want to derive. So this we just discussed is a chemical driving force, right? So we can find this using chemistry means. But we're interested in potential, open circuit potential. That's E of this electrochemical cell. What is the open circuit potential? And it's given by this equation. So if you know the Gibbs free energy of reaction, then this F is Faraday's constant. You know F, you know N. For lithium ions is 1 plus. So this N is equal to 1 for lithium ion batteries. So this is a neat little relationship between electrical open circuit potential and the Gibbs free energy. So I thought, let's discuss this and derive this equation. Okay, so we have, so what we did was, we started off a cell which had electrode A and electrode B, and we had the electrolyte in between. And then we not short circuited, but we, in a way you short circuit through a controlled resistor so you don't have too much current. So at the end, so this is our initial state. A final state was this, where we ended up with the reaction was complete, and this is still the electrolyte. So we ended up with this. And in this process, energy was given off. And how much energy was given off? Delta G of reaction for this case, formation of AB. So this much energy was given off, right? So I want to now derive what is E, that's the open circuit potential of this cell. So let's do a little thought experiment. We went from stage 1 to stage 2, and we gave off chemical energy. Now what if I can reverse the process? So in this reaction, A plus ions moved in this direction, right? A plus. So now I want to push them back in that direction and do it electrically and see how much electrical energy it takes to move this back to that. See, we went from here to there by chemical means, right? So we had chemical driving force. So even though this is electrochemical reaction, but this is the same as A plus B gives you AB, and you know this Gibbs free energy for that reaction by looking at a chemistry handbook, just pure chemistry. But now I'm saying that, okay, we get the same effect when we do this reaction in an electrochemical cell. So we went from 1 to 2 by chemistry. Now let's go from 2 to 1 by applying potential. And the potential we'll apply is E. So how much work does it take to take all the A atoms back to the left side? So let's start with one lithium ion or atom A. You can use either way. So we have AB. I want to push one A ion all the way over there. So how much energy does that one take? So for that, let me say this distance is x. Let me say the potential is E. So what is my electric field? Electric field is E over X, right? Voltage over distance. Now electric field is also force per unit charge, right? That's the definition of electric field. So what is the force on one ion of A plus? What's the force on that? The force would be Q times electric field. See, electric field is force per unit charge. So this, let me say, is electric field symbol I'm using. Electric field is force per unit charge. So the force on this charge will be the charge of the electron plus times electric field, right? The charge on this is 1 electron. One actually positive electron, right? So that's the force. So now I'm moving this ion from here to there, distance x. So work is equal to force times distance, right? That's the work it takes for the A plus to go all the way there. So force times distance. So force we know is QE and the distance is x, right? So now we know that electric field is E over X times X. So this is QE. So to move one ion from here back to where it came from, it took this much energy, QE. Now, in 1 mole of A metal, how many A atoms do we have? We have equal to Avogadro's number. That's 6.02 times 10 to the 23 A atoms. That's how many we have. So work to move 1 mole of A back to where it came from is equal to, let me call this A for Avogadro's number, would be Q times E times A, right? So I just this was for 1 ion. For that many ions, I just multiply by A. That is 6.02, 3 times 10 to the 23. So I can rewrite this as E, or let me write it as, let's see, QA times E. So QA is Faraday's constant. And that's equal to 96500 coulombs per mole. I think it's just coulombs. 96500. So this is a very important value in electrochemistry. So notice we had A plus, so we only had 1 electron removed from A. So in this case, in our calculation, N was equal to 1 because we went from A to A plus. If we went from A to A plus plus, N would be equal to 2, and it would take twice the amount of energy. So to generalize, we multiply by N. So this is the amount of electrical energy it took to send the system back to its original state. So notice it took delta GR to take it from here to there, and to move it back, it took NFE. So they both have to be equal, right? The energy to go from here to there has to equal energy to go from here to back. That's why we can say the chemical driving force energy, the energy it took to go from stage 1 to stage 2 is equal to the electrical energy it took to take it back to state 1. So when you know the Gibbs free energy of the reaction, and you know the number of electrons involved, for A plus N is equal to 1. So for us, for lithium, N will be equal to 1. So if you know the Gibbs free energy for the reaction, we know what the voltage is across the cell. So that's what I wanted to cover in this. And now I want to talk about a very interesting thing, and that is, what is Gibbs free energy? Now, I wouldn't be able to answer the question completely, but I'll make some progress. So by and by, I think we'll answer the question as we go along. And now today's lecture is again a fundamental lecture. So, but I promise you, next time we meet, we'll actually go on a systematic approach to lithium-ion batteries. But so far I'm just laying down the foundation, even though we had done some description of lithium-ion batteries from, I think next time we meet is September 5th, we'll actually start taking a more disciplined approach to lithium-ion batteries. But I want to discuss Gibbs free energy more fundamentally. So I think this will be, so to me, fundamentals are important, because once you have fundamentals, everything falls into place. So I'm going to start from scratch. I'm going to start from the first law of thermodynamics. So the first law of thermodynamics. This is pretty neat stuff. So first law has a system. So in thermodynamics, we have a system. Now, before I go any further, thermodynamics is the easiest subject for engineers, but it's the most difficult to understand because it actually requires understanding. You can't plug and chug in thermodynamics. So I'm not very strong in thermodynamics, but I love the material. Okay, so we have a system and we have a surrounding. So the surrounding surrounds the system, right? And the whole thing is the universe. The universe includes the Earth, the Sun, the solar system, the galaxy, everything. But for us, locally, we have the system and the surrounding. Okay, so what does the first law say? First law says that the internal energy of this system is equal to, we'll call it delta E, or the internal energy change is equal to Q. So this is a change in internal energy E is equal to Q minus PdV. So that's what they write down for the first law. They'll say first law is conservation of energy, right? But we need to do more than that. So the Q is the heat that enters the system from the surrounding. When that happens, the system changes volume by dV. So the system volume changes. So this is the work system does on surrounding. So there's a system, there's a surrounding. Heat enters the system, system does work. So notice, when heat enters the system, internal energy increases, right? If you give me heat, my internal energy will increase. But in that process, I might expand. So that's what people do. When they eat too much, they expand. So Q minus PD. And the expansion does work. So you're working on the environment, you're pushing the environment. So that's the work done by the system on the surrounding. So that's conservation of energy. So that's an important thing. But now Q, so what is internal energy? Internal energy is, let's say if I have a piece of metal, what's internal energy? It's the energy of the atoms vibrating. It's the vibration of the atoms. So internal energy for a gas would be 3 divided by 2 RT, let's see, is there anything else in that? I think it's nRT. N is N the number of moles? I think so. Anyway, the important thing is internal energy is, so whatever it is, internal energy is proportional to temperature in Kelvin. That's the thing. So if I make my system hot, its internal energy will increase. But the thing is, Q, heat, is not a state variable. Meaning, it's, okay, let me show you what that means. Suppose I draw for a gas, I plot PV diagram. So gas has certain volume, a certain pressure. So if I have a position over here, then on the PV, if I say the E value is, let's say, E1 for this, then I can go meandering all over the universe. If I come back over here, I should have the same internal energy. So internal energy is a state variable. So pressure and volume are state variables. So Q is not, right? So if I go around the loop, I'll have a different Q. So Q is not a state variable. We don't like that. We like state variables. So what we did is we concocted another term. So this is our imagination. Enthalpy, which is H. So humankind came up with this enthalpy concept. So this is a figment of our imagination, just to deal with Q, which is not a state variable. So what is enthalpy? We said it's equal to E plus PV. So we came up with this idea. We meaning, I think it was 3 people, Maxwell, remember the famous Maxwell? Carnot engine, and Gibbs, I think. These guys, they had nothing to do but to just BS about thermodynamics. These guys are rich. A lot of these people are rich, So now notice, what do I do? So given this, God knows where it came from, we don't know, but let's use it. So we say delta H is equal to delta E plus P dV, P delta V plus V delta P. Oops, I keep writing D. So I'm doing differentiation, right? Kind of. Engineers can do this. Now notice, this delta E plus P dV, where is my, here, delta E plus P dV, that's Q. So this is Q plus V dP. So my delta H is Q plus dPP. And then if I say that my pressure is constant, if I keep P is equal to constant, I'm back to delta H is equal to Q. So, but delta H is so delta H is a state property because we keep pressure constant. So delta H is equal to Q by keeping pressure constant. So one more thing I want to talk about. So I'm just laying the background to understanding Gibbs free energy. And I think this is interesting stuff. By the way, if you really want to learn thermodynamics, and I think you should, to exercise your brain, I highly recommend you Google Khan Academy. So Google Khan Academy and then Google thermodynamics, because if you spend a weekend, Saturday, Sunday, studying thermodynamics, you'll be a happier person. I can guarantee you that. So if you have to decide between hiking or doing thermodynamics, do thermodynamics. Okay, so we did first law and we did enthalpy. So we did one more thing, and that is entropy. So what the hell is entropy? So entropy is pretty simple. So we say a change in entropy delta S is equal to Q over T, but this Q is for a reversible reaction. It's the same Q, this Q baby over here. So if I give Q to my system at temperature T, then entropy is Q over T. Oh, the change in entropy is Q over T, but the Q has to be reversible. So what do we mean by reversible reaction? Reversible reaction is like this. Suppose I'm at this point, I want to go to that point on a PV curve. So we know that P times V is equal to nRT. Now you did this in high school, right? For a gas, for ideal gas, PV is equal to nIT. So if I have an isothermal system, meaning temperature is constant, then P is inversely proportional to V, right? Or I can say PV product is a constant. So if I were to plot PV on a binary on the scale, the curve would look like this, right? So here I go from state 1 to state 2. P is inversely proportional to V. By isothermal, I mean this. And this is an important thing to know, that if I have, I think the camera can see me over here. If I have a container and if I have a piston and there's gas inside this container, and I'm putting this on a reservoir of infinite size at temperature T. So this is my reservoir. So this gas will always stay at temperature T. And then I put small pebbles on top of this piston. Now the piston will come down and it'll come to equilibrium at this point. Now slowly, so I'm at stage 1 over here. Now slowly I lift these pebbles so the piston will rise up, right? If I decrease the weight on top of my piston, the pebbles will rise up. And I assume that friction coefficient is 0, no friction. So friction is 0, because I want to describe what is a reversible reaction. So as I lift the pebbles, I'll slowly move down this curve, very slowly. So the emphasis on the word slow, because I want to keep the temperature over here, T. I don't want the temperature to change. Now, why would the temperature change? If I were to remove the pebbles, why am I saying the temperature changes? Why does the temperature change? So we know enough thermodynamics now. So as I remove the pebbles, I'm removing pebbles, piston is going up. If I do it in a hurry, as for example, if I were to put the same system with a piston and only put 2 blocks of mass. Too heavy. If I remove one quickly, then it's a sudden reaction, right? Why would the temperature change? The reason is our good old first law of thermodynamics, right? That delta E is equal to Q minus P dV. So this is a system, this is a surrounding. So the system, so the gas is working in the surrounding. So since, and there is no Q coming from outside, so let's suppose we don't let Q come from outside, meaning we have an adiabatic process. So what we do is, instead of connecting to reservoir, we surround this with a blanket. So no Q. So Q from surrounding is equal to 0. So that means delta E is equal to minus P dV, right? So we expanded the gas and no heat came from outside. Notice the internal energy decreased. So delta E decreased. Now delta E is, I mentioned that E is 3/2 nRT. E is proportional temperature. So if delta E decreases, the temperature decreases. So that's what happens in refrigeration. When you have a gas, when the gas expands, gas gets cold, right, in our refrigeration system. So that's the first law of thermodynamics. And so what we're doing over here is we're describing a reversible process. So what we do is we do the reversible process very, very, very slowly. So let me get back to my reversible process. I got distracted. So we remove the pebbles very slowly. So this way, Q can enter from the reservoir and keep the temperature constant. So this curve is for T constant. So we slowly go down this curve. So that's a reversible process. Okay, so where was I over here? Let me just remove this extraneous stuff. So what we have is we have a reversible process where we start at position 1, we go to position 2 very, very slowly. And so the question is, how much work is done? So when we go from position 1 to position 2, we do some work. Oh, okay, fine. So how much work is done? So the amount of work done is the area under this curve. So this is the work done. Why do I write Q over there? So let's see. So what we did is that we have, so this is like pressure 1, volume 1. We're going to pressure 2, volume 2. So the work done is equal to integral from position 1 to position 2 P dV. So now we know from this ideal gas law that P is nRT over V, and then we have dV. So this would be, let me just write down the answer, nRT log V2 over V1. So this is the work done by the system on the surrounding. So this is work done by the system on the surrounding, But notice I said we're on an isothermal line. So temperature is constant. Therefore, internal energy is constant. Therefore, by first law, we have delta E is equal to Q minus P dV. So E is constant, so this is 0. Therefore, P dV, the work we did, is equal to Q. So that's why I wrote Q over here. So Q comes from the surrounding. So Q, number of calories, is fed to the system to keep it at constant temperature while I'm removing pebbles. So this is a reversible system. So now what about okay, so let's get back to our thermodynamics of the entropy portion of it. So we're discussing entropy. So entropy of the universe, which includes all the stars, the sun, everything, is equal to delta S of my poor system over here on the board plus delta S of the surrounding. So we did this little experiment over here where we removed pebbles and we're asking what happened to the entropy of the universe, right? So we did this thought experiment. Did we change the entropy of the universe? So let's see that. Let's see what we did. So delta S, I mentioned gain Q amount of calories, right? So what's the change in entropy of a system? It's Q over T. That's how we define change in entropy. A change in entropy of a system is the heat you provide to the system reversibly divided by temperature. And I mentioned this is a reversible process. So this is the change in the entropy of the system. Now what about the surrounding? Surrounding lost Q calories, right? But the surrounding is also temperature T, right? So what's the answer? So by doing a little thought experiment under reversible conditions, we did not change the entropy of the universe. Thank God for that. Otherwise, it would be a disaster. So what have we learned? That reversible processes do not change the entropy of the universe. But in life, we don't have too many reversible processes, right? We are interested in lithium-ion batteries. We want to produce energy, and we want to know, will the reaction be spontaneous or not? Like if you're making a bomb, you want to know if I mix up those chemicals, will I have a spontaneous reaction? Will I have an explosion or not? So if you want to deal with irreversible reactions. So for that, I'll go to this board. I'll keep this over here. I need that. Okay, so let's discuss irreversible reactions. Oh, I could have kept that over here. Okay. So, should I go back over there? Okay, let me go over here. Okay, so I'm going to draw my system again, and I have a piston. I have gas over here, and this time I'll just put two big blocks of mass on top of the piston to keep the gas down. I still have my reservoir at temperature T, and this time I'm going to, okay, I assume there is friction. So before I said no friction, now I said there is friction. And then I remove this one block, so this will move up, right? But it kind of move up suddenly, and but there'll be also friction over here. So there'll be heat produced by this friction. I still want to go from position 1 to position 2 on this curve, but I have Q heat produced because of friction. But I know that I need to feed some Q, I'll call it this time irreversible. So actually, I do need to provide Q calories to system when I remove one block, just like before. But now, because of friction, I need to provide less Q. So how much heat does the reservoir need to provide to the system? Is equal to Q minus Q friction, and that's QIR. So I need to provide less heat from the reservoir to the system when the system works on the surrounding. So let's rewrite our delta S of the universe. So delta S of the universe is delta S of the system plus delta S of the surrounding, right? So delta S of the system will be, okay, so let me just take a little sidebar over here. So what happens is that we are going from position 1 to position 2, and we are going suddenly. So this curve might look like this. In other words, so remember I said the area under the curve is the work done. So this over here in this dotted thing is the QIR, and this other one is, no, that's Q friction. And this other portion is QIR, but the sum is the same as Q. So the Q of the system will be delta Q over R. So that's the total heat it needs, plus the system provides minus delta Q friction over T. So this is the change in entropy of the universe. So notice that this term is bigger than this term, because remember the friction part is in blue and this red part is the, I'm sorry, friction part is QIR, which is heat going up into the reservoir, and QF is the friction. So this term is smaller than this term. So this is greater than 0. So that's another theorem that for irreversible processes, delta S universe is greater than 0. So this is a spontaneous reaction. So for spontaneous reactions, the entropy of the universe increases. So what has all this got to do with Gibbs free energy? Actually, we're almost there. Okay, so now we will tie this and find out what the hell is Gibbs free energy. So Gibbs free energy comes about like so. So let me rewrite the delta S of the universe. So delta S universe is equal to, I said, delta S of the system, delta S of the system, and then I write down minus QIR over T. So what I did was I just put this back. Instead of writing delta Q over R, I put it as delta S system back again. So this is what I have. So what is QIR? So I need to put that in some decent form. So I go back to my favorite thing called enthalpy, which is E plus PV. So we did this before, right? So I differentiate this. Delta H is equal to delta E plus P dV plus V dP, right? And this we know from before, we know from the first law that this is Q. And if we keep pressure constant, okay, so let me rewrite this. Delta H is equal to Q plus V dP. Now, if P is constant, then delta H is equal to Q, right? So what I'm trying to do over here is replace this with delta H. So let me rewrite that top equation. So delta S surrounding cis universe is equal to delta S system minus, I replace Q with this QIR with delta H over T, and I'm saying that I can also write that as delta S system approximately, because this is what's entering the system, right? And we're saying that this is greater than 0 for a spontaneous reaction. So now let me rearrange these terms. I can multiply by T, so I can say T times delta S system minus delta H system is greater than 0. Then I can write delta H system minus T delta S system is less than 0 for spontaneous reaction. So in a chemical reaction, we can find out what is delta H, what is delta S. If it's less than 0, then the reaction is spontaneous. So instead of writing this every time, we just replace it by delta G system. And so we basically take H minus Ts and we just simplify it. So instead of writing delta H minus T delta S every time, we replace it with delta G. That's Gibbs free energy. So what did we do? So we started the lecture by saying there's a chemical reaction, and you can look up the chemical handbooks and find out what is the delta G for that reaction. And then once you know delta G, what do you do with that? And we said that once you know delta G for the reaction, you can put it equal to NFE. So you know delta G, you know number of electrons on that ion, you know Faraday's constant, so you can calculate the open circuit voltage for that reaction. So that's what it did today, and we understood what is delta G from fundamentals. So we did the first law of thermodynamics. Oh, did we do the second law of thermodynamics? Yep, we did. We said that the entropy of the universe always increases for a reaction or it stays the same. The entropy of the universe does not ever decrease. So by me standing here for an hour, I increase the entropy of the universe. That's what the second law of thermodynamics says. So this is the second law of thermo. So isn't life beautiful? We did the first law of thermo, we did the second law of thermo, and we showed that there's a relationship between electrode potential and Gibbs free energy. So when you look at the lithium-ion battery books, you'll find, so the thing you have to ask yourself is, where does voltage come from? How does chemical reaction produce voltage? So this is what we did today. We showed how a chemical reaction can produce a voltage. And we went on a big sidebar through the first law, second law, and so we got to this equation. So now, you can, what we learned today, you can try out this simple test. So do a thought experiment. You have a hot container and a cold container. Why does heat flow from the hot container to the cold container? You can use the first law and the second law of thermodynamics to prove why heat flows from hot to cold. We already did, why does gas cool down when you expand it? And we use the first law. So to explain why heat flows from hot to cold, you use the concept of entropy. You use this kind of idea. So notice, okay, so we have a couple of minutes. So let's explain why heat flows from hot to cold. Isn't this fun? So we can do that quickly. So I have two containers, and they are in thermal contact. Here's container 1. Here's container 2. One is hot. So this is at T2. This is T1. So this is hot. And this is cold. So we know heat flows like this, right? So what's the entropy change for the hot container? It is minus Q over T2, right? What's the entropy change for the cold container? It's plus Q over T1. So what's the total entropy change? You add the two, so you bring Q on the outside. It's 1 over T1 minus 1 over T2. So T1 is small, and T2 is large, so this is greater than 0. That means it's a spontaneous reaction. So that's why heat flows from hot to cold. Okay, on that note, I'll stop. So the next lecture will be on September the 5th, Tuesday, same time. Thanks.